So, we shall continue with our procedure to obtain the overall loss coefficient. We have expressed the loss from the plate to the cover 1, and if you consider the top plate from which the loss is taking place directly to the ambient, the radiative heat transfer coefficient from the cover 2 to the ambient, which we shall designate as HR C2 A. Now, we have already expressed that this radiative loss is to T sky and not T ambient. But since everything we want to write it as overall loss coefficient multiplied by T p minus T a or T f minus T a or T f I minus T a, we would like to base it with respect to the ambient temperature. So, we can write down H r C 2 A is epsilon C 2 times sigma T C 2 plus T s times T C 2 square plus T s square times T C 2 minus T s upon T C 2 minus T a. Now, do not worry about this long expression, you can easily work out this. What all we tried to do was the radiative loss with a heat transfer coefficient of HRC2A from TC2 to TA has been expressed as equivalent to epsilon C2 sigma into TC2 to the power 4 minus Ts or T sky to the power 4, which is nothing but epsilon C2 sigma times TC2 plus Ts times TC2 square plus Ts times TC2 minus Ts. So, this is artificially written as if HRC2A, if it is multiplied by TC2 minus TA, it will give me the actual radiative loss from TC2 to T sky. So, that in my overall heat loss coefficient, this is based with reference to a temperature above the ambient temperature T a. Now, T s is given by 0.0552 T a to the power 1.5, where T s and T a are in Kelvin. In other words, this is a estimate. You measure the ambient temperature and you measure the temperature of, let us say, water kept outside, which is cooler than the ambient, and from there you estimate the heat loss, and that should have been lost by infrared radiation from the body under consideration, thereby giving you an estimate of T sky. In other words, you would have reached a lower temperature for the water in the bucket in the evening when there is no sunshine, compared to the ambient temperature if the sky temperature had been so much, and the loss is given by the amount epsilon C2 T sky to the T water to the power 4 minus T sky to the power 4. And of course, there is a simpler relation also. Simply T sky is nothing but ambient minus 6 degrees, works reasonably well. So, my resistance now R 1 upon wind heat transfer coefficient already known to us, by the radiative loss coefficient HRC2A. HRC2A is like exactly HPC1A or HRC1C2, all the other radiative coefficients. Since the loss takes place to the sky temperature, it has been sort of normalized with respect to Tc2 minus Ta rather than Tc2 and T sky. So, now we can express R2 as sorry So, it is the summation of the convective heat transfer coefficient between cover 1 and cover 2 and the radiative heat transfer coefficient between cover 1 and cover 2. Okay. So, you can again write HR C1 C2 as sigma Tc1 plus Tc2 times this is exactly similar to HR P C1, where we wrote Tp plus Tc1 into Tp squared plus Tc1 squared upon the corresponding emissivities. So, now we are in a position to calculate the loss coefficient from the top ut as summation of the resistances R1, R2, R3 inverted. That will be corresponding to the second figure in the thermal network. First one is showing the parallel paths, the second one all of them in series equivalently expressed as R1, R2, R3. And the bottom loss coefficient UB is straightforward. R4 plus R5, R4 is the conduction resistance and R5 is the convective plus radiation resistance, and R4 is given by L upon K, where L is the thickness of the insulation and K is the thermal conductivity. Of the insulation. Okay. And usually R5 is neglected, because Tb is almost pretty close to Ta. So, back-loss coefficient Ub is simply given by 1 upon R4 equal to K by L. Now, my overall loss coefficient UL equal to UB plus UT. Of course, there will be exceptions. UL will not be equal to UT plus UB if the working fluid comes in contact comes in direct contact with a heat losing surface. In other words, all that is being considered as U T is not a loss, a part of it is going to the fluid also. So, we shall come to that type of collector configurations little later, at least one of them. So, having done these things, what did we do? We assumed a single node T p, T c 1, T c 2. From here it loses by radiation to T sky, and there are parallel convection and radiation, and then the back temperature T b to T a, radiation and convection, and by conduction from plate temperature T p to T b, right. So, we estimated, of course, this R 5 is neglected, that means no heat loss by convection radiation from the bottom, and we found out U b is equal to K upon L, and U t is 1 upon R 1 plus R 2 plus R 3, where the resistances R 1, R 2, R 3 are the convection plus radiation resistances between the plate and the cover 1, and between cover 1 and cover 2, and cover 2 to ambient. If there is only one cover, we will not worry about R 1, and it will be only R 2 and R 3. So, how do we estimate now U L? The idea is you need R 1, R 2, R 3, R 4. R 4 is simple, it is L by K. So, we shall want to estimate this U L. Now, the convective heat transfer coefficient H p to C 1, H C 1 to C 2, and of course, H w are known. Our heat transfer knowledge gives us to method to calculate the convective heat transfer coefficient between the plate and a parallel cover 1, between cover 1 and cover 2, and the wind heat transfer coefficient, which we have already given. Now, which we also have got H r P 2 C 1, H r C 1 to C 2, and H r C 2 to ambient. These are radiative heat transfer coefficient, which in general H r multiplied by some delta T gives the radiative loss. Though we know that the radiative loss is proportional to the difference of the fourth power of the temperature. This has been expressed similar to that of convective loss. Then nonlinearity is absorbed in the definitions of the radiative heat transfer coefficient. Even within the framework of properties being independent of temperature, that means the thermal conductivity does not change, heat transfer coefficients we have a method of estimating it, and the viscosity, density, or they do not change with temperature. But even with all these assumptions, my HR P2 C1, HR C1 C2 and HR C2A, they are functions of T. In other words, we need Tp, Tc1, Tc2, Ta, and of course, T sky. This Ta is a metallurgical property which we know. T sky can be estimated from the relations. So, these are not issues, but Tp, Tc1, Tc2 have to be known in order to calculate my radiative transfer coefficient from the plate to the cover 1 or cover 1 to cover 2 or cover 2 to ambient. So, now we have got an interesting problem. Unless we know Tc1 and Tc2, we cannot estimate HRs in general. Maybe I can add a Tp also. Okay, Ta is known to. So, radiative heat transfer coefficients cannot be estimated unless I know the temperatures, and temperatures cannot be estimated unless we know the heat transfer coefficients. So, it is a tricky situation. What do we do now? Of course, you might ask me, what about Ta? I am sorry, what about Tp, the plate temperature? So, this is assume known, because this is an operating condition. So, if a solar collector is operating to deliver energy at a certain temperature, we will be having that temperature to be the corresponding plate temperature, which will depend upon the internal resistances, which we need to know the theory. So, Tp is assumed to be known for a given application, or alternately we are trying to estimate the overall loss coefficient for a number of values of Tp, and we will pick up the appropriate overall loss coefficient depending upon the actual operating condition. So, even if Tp is assumed as an operating condition, Tc1 and Tc2 are essential to calculate UL through various resistances. So, this naturally involves a trial and error or an iterative procedure. Right. So, step number 1, we will guess Tc1. Let the first guess be Tc1 1. So, in case my first guess is not correct, I will go to second. If second one is not correct, I will go to third, so on and so forth, and we will try to iterate, and we set up a procedure or the principle behind iterating this section. So, the first step is T p is known, let us write it down, T p known. So, I guess T c 1 and the first guess is designated as T c 1 1. So, calculate Q loss top, and this is, since I am using the guess 1, I will qualify it with a superscript of 1, which will be H p C 1 plus H r p C 1 1, because it is obtained with T c 1 1 times T p minus T c 1 1. So, let us be very clear, we guessed a value for T c 1 as T c 1 1. The loss that is obtained from plate to cover, because I know the plate temperature, is the convective heat transfer coefficient plus the radiative heat transfer coefficient estimated with the guessed temperature of T c 1 1 multiplied by T p times T c 1 1. Now, having this Q loss top is the same estimated as from plate to cover 1 or cover 1 to cover 2 or cover 2 to ambient, and the sky part which we have already taken care of in defining the radiative heat transfer coefficient. So, let us estimate this Q loss top will help us estimate T c 2. Again I will qualify it with a superscript 1, that is T c 2 1 obtained with Q loss top 1 with T c 1 1. So, this relation will be Q loss top 1 should be equal to H p C 1 plus H r p C 1 1 times T p minus T c 1 1 should be the same as H C 1 to C 2 plus H r C 1 to C 2. Again I shall qualify it with a superscript 1, because it follows from my first guess, times T c 1 1 minus T c 2. Everything is known here except T c 2. So, this enables us calculate T c 2. Now, from this Q loss top 2, because Q loss 1 is T p to T c 1 1, which we have guessed, the same amount of energy should be going from cover 1 to cover 2. Now, from the top cover I will get a different number, which will be H w plus H r C 2 a times T c 2 1 minus T a. If you want to be precise, we can call this H r C 2 a 1, because this has made use of TC2 1. So, now what is the difference between these two? This is the loss taking place from cover 1 to the plate to the cover 1, and that should be the same as cover 1 to cover 2, which enabled us to calculate TC2, and from the TC2 my guessing is over, and I should be able to calculate what will be the top loss from the outer cover to the ambient by convection and by radiation. And this radiative heat transfer coefficient is calculated based upon T sky, T ambient and TC2 dashed. So, I compare these two, and if we have Q loss top 1 minus Q loss top 2 by any one of them, in fact it does not matter when they converge. Here I put a modulus sign, so that we really do not know whether Q loss top 2 is higher or less, but our idea is, let us say this should be less than 0.05. That means, the difference in the guessed heat transfer from the top because of a guessed cover temperature should balance with whatever is the outgoing heat loss. As a consequence, these two should not differ by more than 5%. I may set it as 2%, 10% depending upon the accuracy that we need. If this is satisfied and TC1 1 and TC2 1 are acceptable. If not, if it is greater than 5%, (0.05) say, then change instead of TC 1 1, change to TC 1 2, which will be some TC 1 1 plus or minus delta t. So, I change the initial guess by an amount of delta t, and one can physically argue if Q loss top is higher than Q loss 1, whether TC 1 should be increased or decreased. So, that physical check one can do and go in the right direction. So, this is a sort of involved calculation, and it requires iterations unless you know the guessed values, and you have to on top of it most of the time HPC1 and HC1C2 are the free convective heat transfer coefficients, which themselves will depend upon the temperatures. So, if they start changing, the overall loss coefficient may not be different looking, but my individual component convection and radiation losses can be quite different. However, this procedure is can be in a routine in a simulation package, and one can calculate the overall loss coefficient. To make our life a bit easier, a correlation for UT has been developed, and this is by Klein once again from University of Wisconsin Madison. And so, the iterative procedure may be called cumbersome, and particularly the heat transfer coefficients involved or free convective heat transfer coefficients, they also depend on the temperature. Though in this particular instance, which we assume we use the current HPC1 or HC1C2. So, this is a long expression ut. I shall write it down so that you can also note down. I shall give a printed handout so that the deficiency, if any, by handwriting hopefully will not be there in the printout. Okay. So, this looks a really difficult relation. I am not sure whether the iterative procedure takes time, less time, or this relation, and it is not all, where of course n is the number of glass covers. So, you can calculate for one glass cover or two glass covers, but the assumption is epsilon C1 equal to epsilon C2 equal to epsilon G. The relation you will find is written in terms of epsilon G. Then F is another expression then the constant C 520 into 1 minus 0.4051 beta square, and this is for 0 less than beta less than 70 degrees, and for 70 degrees less than beta less than 90 degrees use beta is equal to 70 degrees. Then E is a 0.43 to 1 minus 100 by TPM. Beta of course is the tilt in degrees. TA this should be in Kelvin. and TPM mean plate temperature, again in Kelvin, and HW the wind heat transfer coefficient in watts per meter square degree centigrade. So, there is a convenient method of calculating the overall loss coefficient, which will involve an iterative procedure by guessing the cover temperatures for a given operating condition, or the top loss coefficient can be calculated by the correlation due to Klein, though it is a long expression, it does not involve iterative calculations. So, basically what we did today is gave few configurations for liquid based solar collectors and qualitatively assessed what is the temperature variation in the direction of the flow and in the direction perpendicular to the flow direction, and then we made a number of assumptions in the analysis, most important being steady state and the properties do not change, and the n number of other 14 assumptions, and treating the 2-dimensional problem as 2 1-dimensional problems. Then we have expressed the thermal network to calculate the overall loss coefficient, and then a simple correlation to calculate the top loss coefficient has been proposed by a Klein, simple in the sense the expression is complicated, but does not require any iterative calculation. So, what we shall do is, what is the now temperature variation in the solar collector liquid based. Okay. Now, what you have got is something like this. We say this is x and this is y. If I take exaggerated this is a inner diameter some d naught and inner d, let the thickness of the sheet be delta, and this tube is joined with a solder or some bondage. So, this is the mid plane and this is the mid plane. So, I have to have a simple some w minus d by 2, or w is the distance between the center to center, and we have got a number of elements repeated like this in the collector. They are all joined and each one is a half a sheet on this side and half a sheet on the other side, with a tube in between. And if we plot the temperature in the x direction, heat is flowing towards the tube, which is at Tf, which is lower than Tp. So, the temperature is highest at the symmetric plane, because again it will continue like this, then another tube, again it will continue like that. Okay. So, we have taken a half a sheet on this side and another half a sheet on this side for a particular tube. This is in the x direction. We are saying that the temperature around the periphery is negligible. So, this is a constant temperature. If I take this picture, that seems to be too much, right, and if I go in the direction of x, so this will be increasing like this as I go along L, because it is gaining temperature. So, if I plot it with respect to y and t, this will be at the beginning of the collector, this may be t on the sheet at fixed x. Now, this may be T f, which will be entering at T f y and exiting at T f o. So, this is the temperature variation in the y direction at a fixed x, and whether it is high or low depends upon whether it is a fluid region in the tube or the fin region and where we are. And in the x direction, it is maximum at the mid plane of the sheet and uniform temperature across the tube, and again it increases, that element is reproduced. So, we can analyze this particular element. So, temperature distribution between the tubes and the collector efficiency factor. So, that is what I have already shown the picture. So, that is what the picture is. So, this is one half I will show of some thickness delta, and here is the tube with inner diameter or d I and outer diameter d naught, and this continues of course, and here is the bond. Let this thickness be delta, and if we center of the tube to the center of the sheet, half of it, that will be W by 2, and if this is a D capital, this will be W minus D by 2. So, let us see this is my x. So, center of the tube to the symmetric plane is W by 2. The distance between the symmetric plane and the beginning of the tube is hence W minus D by 2, if capital T is the diameter. It is given by some bond conductance, and then at the base will be a temperature of T b. Inside will be T f, right. Over here it will be a T x, all right. Now, if we take this repetitive element, because of symmetry, the also called insulated, that is, since dt dx equal to 0 at x is equal to 0 of the previous picture. So, if I just forget about the tube part, this is my base temperature T b, this is the insulated portion, or dt dx 0, and this is my W minus D by 2. Okay. And here is the incoming solar radiation. And here I measure my x. I take a elemental volume of width or length or delta x, and of course, this is delta. So, I shall just make the energy balance. If I once again this is the control element, those of you who are familiar with the heat transfer course, you know that this type of analysis has been done a large number of times, and here enters minus k delta dt dx at x, and what goes is minus k delta dt dx at x plus delta x, and what comes on to this is s times delta x, and what goes out is u l times delta x into T minus T a. So, I can write enter minus k delta dt dx at x absorbs s times delta x loses UL delta x t, technically a function of x, minus T A, and leaves minus k delta dt dx at x plus delta x. Okay. So, this is what we are having, and if we want to make a energy balance, and we are assuming unit length perpendicular to plane of the board or screen. So, S into delta x enters plus minus U L into T minus T A leaves plus minus k delta dt dx enters, and then leaves minus k delta dt dx at x plus delta x. This should be equal to 0. I prefer to write this equation just not as an equivalent, but in terms of physics. This is an entering radiation that is absorbed, and U L into T minus T A leaves, it is a loss, and on one side the entering is given by Fourier law of conduction minus k delta dt dx, and what presumably leaves the control element is the same thing at x plus delta x. So, there is a minus sign. Now, the gradient of dt dx is going to take care of whether this is positive or this is larger, this is smaller, etc. This minus k delta dt dx at x plus delta x equal to minus k delta dt dx at x plus d by dx of minus k delta dt dx into delta x. So, if you plug in these values, you will get so this second derivative comes from that d dx of minus k delta dt dx, and if I equate that, this is what we will have, and this is a second order equation, requires two boundary conditions, which will be dt by dx is equal to 0 at x is equal to 0, t equal to T b at x is equal to w minus d by 2. At the base of the tube, this is given by w minus d by 2, x is equal to, and it is T b. And by virtue of symmetry, we call the insulated thing as heat transfer terminology, because dt dx is 0. And if you introduced m squared equal to u l upon k delta and a psi equal to t minus T a minus S upon U L. This becomes and the boundary conditions in terms of psi being so we have set up an equation in the x direction. We had considered half of a repetitive element from the midplane of the sheet up to the beginning of the tube, and you should be familiar with this equation in heat transfer. It is nothing but exactly the Finn equation. Okay? And you can see that m squared is u l upon k delta, and in Finn case m squared is h into p upon k a. So, you have a length dimension extra here and another length dimension extra here. Instead of that, you will have u l by k delta in this case. Otherwise, it is nothing but the Finn equation. We will try to get the solution in the next lecture, and until then,